So hi everyone, thank you very much for being here. So today we'll be talking about self-supervised learning and DynaV2. I explain a bit what is self-supervised learning in general, and we'll work our way towards DynaV2 and some more recent work around self-supervised learning. So you'll understand a bit how it works, what it can be used for, etc. Now, I was going to say a few words about myself, but you introduced me very nicely. Basically, I just graduated my PhD. I'm an incoming researcher at Meta now. I was advised by Maxime Ocard, Piotr Bojanowski, and Julien Méral. Before that, I worked, I was a master's student. Before that, I was at École Polytechnique and ENS in Paris. So most of my work on self-supervised learning in vision transformers, basically. That's my topics of research. Today, we'll be talking mostly about self-supervised learning. So yeah, these two things mostly. The first thing to answer is what is self-supervised learning? You might know about supervised learning, which is when you have data and labels, and unsupervised learning, when you have only data, you have no labels. For example, in the case of vision, you have image and labels, or you have only images. Well, the first answer is that self-supervised learning is unsupervised learning. In a first approximation, it's unsupervised learning, and you can just remember that as a first approximation. Now, of course, as you might expect, there's a bit of subtlety in there, but really self-supervised learning is a type of unsupervised learning. You have only data. Now, if we want to go one step further and try to give a second order approximation, let's recall the idea of supervised learning in general. You've got this X data and this Y, which is your label. And to train a model, your model is this function F, this block, this yellow block. You need to compute a loss. You need to compute a loss to be able to backpropagate the gradient, etc. Now, to give a more specific example, to have a more visual explanation, your data might look like an image, and the label might be saying, well, this is an image of a dog, and your model will have a prediction. The prediction might say it's a cat, and the loss will say whether it's true or not. And then you will have a backpropagation of the signal through the weights of the model that will update the model, and this way the model will be learning. That's the learning process. That's where the magic happens. The question is, how do you do this whole thing? Well, you don't have a Y. You have no label, you have only images. How do you do this thing? That's where self-supervised learning comes in. And the idea, trick, is we're going to try to create a fake label from the data. We have an initial X, as you can see here, and we're going to create a pseudo X and a pseudo Y, which are going to be the pseudo data and labels for our task at hand. To give a more visual explanation, for example, we could talk about colorization. You have an image, and if you have just a data set of images, you have all you need to train a model for colorization. Why? Because your X tilde, your pseudo data, could be the grayscale image, which is very easy to compute from the color image. And the Y, the equivalent to the label, is the color. And so you have this information just from the data again. And so you have this whole thing. The model will output a prediction, and you will have a gradient, and you will be able to learn a model. With only images, you are able to learn to train a model that will learn to do image colorization. So image colorization, in this sense, is a self-supervised learning task. Now, you might say, okay, that's very nice. Get the gist of what's going on. That's very nice, but what if I don't care about colorization? This is a nice thing, but it's a bit limited. What's the goal? The goal is, I can't see the messages, so please interrupt me if there's something important or question. The main goal is representation learning. Now, what is representation learning? Why are we doing this? It's just basically the concept of converting an image to a vector. For example, here you've got an image of our very own God, and you convert it to a vector, to a model. And this vector, you hope, is going to be a good vector. It's going to be a good representation of what's in the image. What do we mean by that? For example, if we want to find other images of Yann LeCun, well, we just need to find images that have a similar vector. Similar in terms of just distance in this vector space. Same thing, if we want to cluster images, we can do a k-means on vectors. That's the whole point, because images is hard to analyze, but vectors, they are very nice. We know how to do a lot of things on vectors. As I was saying, if we want to cluster vectors, we can just do k-means. If we want to do classification on vectors, we can do logistic regression. All of these are very simple tasks to do. And so if we can convert an image to a good vector, every task on images, classification, clustering, whatever, becomes super easy. You're just pre-processing your images, pre-digesting them, so that everything you do later will be super easy to do. I'm hearing something, but okay, someone has his mic on. Now, this is basically the concept of representation learning. As you might expect, it's not that easy, but that's the reason we're doing it. For example, in the concept of colorization we were discussing earlier, we do colorization not because we care about colorizing images, but because by learning to color images, model will learn internal representations, internal activation patterns that are useful for representation learning. We can just take the intermediate activations, and that will be an interesting representation of the images. Now, why would you do that with self-supervised learning? Because we have supervised learning. The first thing is the scale. When you do self-supervised learning, you can pre-train on any image you want, and that's a very appealing thing. You don't need any label, and there's a ton of images on the web. By doing self-supervised learning, you can scale up. This on the left is a depiction of the quantity of images in ImageNet. ImageNet is pretty big if you know about it. It was a very big thing in vision for last 10 years. It's about 1 million images. There's a ton more images on the internet, like a ton. If we could exploit all this data, it would be very nice. Of course, there's a lot of problems of getting the data. You don't want to scrape too hard, etc. But still, that's a lot of data, and it's nice to be able to use all the data you want. Another thing is about how to access label. The thing is, we're used to nature images. On nature images, it's very easy to get labels. In this case, for example, it's very easy to just ask anyone on the street, is this a hot dog? Is this not a hot dog? You get labels. You have your annotated data set super easily. Question is, how about this kind of images? Look at it and tell me whether this patient is healthy or not. Does he have a tumor or not? I don't know. I literally don't know. I don't remember where I got this image from. I cannot annotate this image, and you cannot. I guess maybe some of you can. To annotate this image, you need to have a doctor. And the problem with doctor is not that they're hard to find, it's that they are expensive. When you have nature images, you don't do that, but some people pay very low wages to annotate just natural data. For medical images, you won't have a choice. The doctor is just going to tell you his price, and the price is high. And the price being high means you will get very few data because you have a limited budget. And so the quantity of medical annotated data is very limited in the world. So, however, the quantity of unannotated medical data, there's a ton of those. So for medical data, for example, self-supervised learning is super useful. You can exploit this mass of unlabeled images, and that's super interesting. Now that you've got the gist of what is self-supervised learning, why do we want to do it? The question is, how do we do it? Of course, I've mentioned colorization to give you an idea of how it works. Colorization was actually a self-supervised learning approach 2 years ago. Now it's not really the main thing. Now you've got much better approaches. And most approaches fall into a general class that is called contrastive learning. Let's try to describe what is contrastive learning. The idea is very simple. You've got an image on the left like this, and you're gonna create two different crops of this image, two different versions of this image. One, for example, is gonna be cropped at the top, one at the bottom. It's random. One might be grayscale, or you might just tweak a bit the color of the other, this kind of things. Just you apply some light modifications. And as you can see, these two images are still depicting kind of the same thing, same building. And you might want a model to understand that they are depicting a very similar thing. The output of the model for these two images should be pretty similar if the model understands the images. The fact that we put it in grayscale or that we increase the saturation or brightness shouldn't modify it. The fact that we took only the top of the building or the bottom of the building does not change the building that it's part of. So we would like the model to give the same or similar output for these two images. And so we'll feed these two images through our model, and we will have our loss and objective that tries to attract the two outputs. These two outputs are what I depicted here as H1 and H2. We'll attract these two vectors. Now, there is a small issue here. You might have noticed it. There is a problem, which is that if you just do that, there's a trivial solution. The model will just output the same thing for all images, for example, all 0. And if the model just outputs 0 for every image, well, the loss is solved, the task is solved, the objective, the model takes the loss to 0, but does not learn anything, basically. It didn't learn to recognize images at all. So, question, how do you prevent that? And the trick is, I mean, there are many tricks, but the most common trick is you add a contrastive loss. You balance out attraction and repulsion by adding a loss where you push away with a different image. And now, for example, you have this third image that is unrelated to the two first images. And so you know you want the model to have a different output for H2 and H3. And so you push away H2 and H3 while you push together H1 and H2. And this way, you get a model that will need to have diverse outputs. It cannot always output the same thing. But we need to have outputs that are pretty close for images that are semantically similar, that are depicting approximately the same thing. Here I took as an example a building, but it could be, for example, a picture of a cat, and the crops would be showing a cat ear and a cat tail. And the model will need to recognize that although these do not look the same at all, they are part of a cat. They are semantically similar. They depict the same thing. So that's the trick. And this is, if you think about it, if you take just an instant to look at it, it's very simple. It is a super simple idea, and it works super well. This simplified, like the base setup was described in a paper called SimClear, Simple Contrastive Learning, basically. And super good, just works super well. Most methods for self-supervised learning of representations nowadays are based on kind of the same. DynaV2 is based on something very related to that, something that is very close to that. Now that we've got all of the basis of self-supervised learning, etc., we can actually go on to talk about DynaV2. DynaV2 is a work that we conducted with my advisors and other colleagues at Meta a few years ago. Now it's been 2 years and a bit. It's a self-supervised learning model, actually a family of self-supervised learning models. And so what I'm going to do is try to explain to you how we got there, what was the objective, and what is the recipe to how do you get there as a project, and also what does the model look like and what is it good for. First thing is, how did we start this? The idea was we just wanted to build a very general vision model, something that you can use to do classification, segmentation on very varied type of images, We just want one model that can handle all of images. We want the model to be usable as a frozen encoder. That's something that's just a choice, but some vision models are meant to be fine-tuned, to be trained further on specific domains, on specific tasks. The idea of DynoV2 is to make it so that without even fine-tuning it, it's still very good. And we are trying to do that with self-supervised learning, without supervision. One thing is that doing it without supervision means it is less specialized on the specific labels that we give it. And so it's super general. The features stay very general, can be used for a lot of things. And so that's what we wanted to do. Now, the recipe is really that. It's very empirical. The recipe for DynoV2 is basically that we took what existed and what worked, and we scaled it up. What do we mean by that? We first took a lot of images. We scaled up on a ton of images, but we took about 1.3 billion images, and we filtered these images. We're going to go back to this point a bit later, but we filtered these images down to a lot less, like 10 times less images to have the good ones, and we trained on those images. We trained with things that existed. We're going to detail a bit the methods that we use, but basically we did not invent a self-supervised learning objective. It was not needed. What was needed is to scale up big data, existing methods. Big model, big giants is 1 billion parameters, which is small, especially by today's language model standards. But for the time and for vision was pretty big. And now that we've got this big giant, we also did something that is called distillation. Distillation meaning we try to squeeze all of the information and all the capabilities of the big model into smaller models. We did fine-tuning specifically for higher resolution. And one thing that I include always is elbow grease, which by that I mean basically just tweaking everything hard. Just a lot of effort, a lot of attention to detail. And that seems dumb, and that seems, I mean, that might seem like it's out of place for like a scientific recipe, but it's honestly, you would be surprised how much in this kind of big works is just a ton of how much you tweak things, how much you optimize, you work on refining your recipes, refining your hyperparameters, your choices of design choices of components, etc. Now that we got this, let's discuss a bit the DynoV2 objective. DynoV2 objective looks like that. That's how you train it. You train it with the loss that is the sum of 3 different losses: Dyno, ibot, and Cohere. The Dyno loss is very similar to contrastive learning. That's what we discussed earlier. You push together images that are related, that are from the same image, and you push away images that are unrelated. Dyno is slightly different to what I showed to you, in the sense that it does not use the same mechanism to push away unrelated images, but apart from that, it's very similar. You've got also Cohere. Cohere is a smaller regularization. Honestly, you can mostly ignore it. It's basically trying to make embeddings uniform in the hypersphere, just spread embeddings in the embedding space. ibot is a third loss that is basically mass image modeling. We'll come back to mass image modeling later, but it's mass image modeling in the latent space. These are the 3 components. But as I said, I did not invent these 3 things. These 3 things existed in the literature. DynoV2 is about just combining things, scaling them up carefully. So let's discuss a bit scaling up. Why do we scale up? Scaling up is basically a given. When you do self-supervised learning, it's kind of the first thing you think of. Because you don't need labeled data, you'll be able to use all the data you can find, and you will be able to scale up a ton. The thing is, people have thought about it, of course. It didn't work at first. A lot of people have tried doing that, and the results were not that great. This was not clear why. A lot of people were surprised and were a bit annoyed at that. But the first conclusion we can draw from that is that it's not straightforward. It's not that easy. although it seems obvious that you should do that, just trying that dumbly will not work super easily. Why is that the case? It's very hard to say, honestly. But the answer that we try to give as a hypothesis in DynaV2 is about curation. Basically, just training on every image you can find on the internet is not a good idea because a ton of images are bad, just really uninteresting. And because if you train on everything you find, you will end up training on disproportionately on some things. For example, if you train on everything you find on the internet, you're going to train on a ton of pictures of t-shirts on a white background because you're going to train on Amazon images, which are super uninteresting. Just your model is going to overfit on that. You don't care about that. So your model is just going to lose time on these things. You need to curate your data. In NLP, it's super, super important. This was the data mix for Llama. It's a super careful mix of data. This was Llama 1. I don't think we have public data for data mixes for more recent Llamas. There's probably some stuff for DeepSeek. I should look at it. In Vision, it's been the case too, but it's less common. You have the clip work that did a lot of curation, but it was not reused that much. So we need to curate. So we try to give our own answer to the question of curation. And the way we did curation is we introduced an automatic pipeline. This is what we did. We start from a good small data set. Why do we do that? Because we know that our methods, I know, etc., they work on ImageNet. They were designed for it, and DynaV1 was trained on ImageNet. We know it works. What we're going to do is to try and train on ImageNet that we augment, that we make bigger using images from the internet. We have this small pool of images, ImageNet. It's created, it's nice. And we have this large pool of uncreated images that are just messy images from the internet. And what we're going to do is we embed everything to a vector space using DynaV2 or something like that. And then we retrieve similar images. For each image in ImageNet, we find the nearest neighbors in this dataset. And we see, okay, those are images, other images of food, that's great. And by just adding that on top of ImageNet, we get an augmented version of it that is bigger. We do that not only with ImageNet, but with multiple datasets. And we get this dataset we call LVD142. It's 142 million images that have a pretty nice distribution. So here in this example, we're showing that if we are looking for pictures of food, get more pictures of food. You forget about pictures of cars, for example. 142 million high-quality images, and that's super nice. This is the way we did curation in DynaV2. Now, what does it look like in practice? Well, the results are pretty good. These are a lot of plots. And also, I need to emphasize that those are results from the paper, so they are comparing at the time, so a bit more than 2 years ago. I'll say a bit more how it compares today. First thing is, compared to previous self-supervised learning methods, we depict those previous self-supervised learning models in orange. DynaV2 is better. So at different model sizes, here the x-axis is different model sizes. Flops is a measure of how computationally intensive a model is. So this is a bit small, 20 million parameters, and this is a bit giant, 1 billion. At every model size, DynaV2 and on every task, DynaV2 is much better than the previous SM model. Now, if you compare to clip models, the pink ones, clip models are super good on classification. It's debatable, basically, compared to DynaV2. On some datasets, it's quite close, quite tight. Although DynaV2 has these small versions of the models, which are very nice, which are not available with clip. For segmentation, depth, retrieval, a few tasks. There are a few tasks where just DynaV2 is much better than all the clip models that exist. Now, again, this was a comparison at the time we released DynaV2. How does it look like today? There's no self-supervised learning model that is that beats DynaV2. In terms of clip or clip-style models, there are better models now. And I think for things like classification, you would want to use a clip now. things like, I don't know, Siglib V2 or whatever. There are some recent models that are pretty good. But for segmentation or depth estimation, in the specific setting we're discussing here, so we mean with frozen feature maps. So to produce good feature maps, DynoV2 is basically unchallenged. It's actually a good question why, but Flip models don't produce very good feature maps, whereas DynoV2 gets super good feature maps. Now, these are the main results. Before we get on to the next part, these are the lines of code you can use to load DynoV2. It's super simple. If you've never used Torch or just done that, I really encourage you to play around with this. Just after you import Torch in just one line of code, you get a DynoV2 model in a notebook. You can use Google Colab. It's very easy. Just load it up, take an image, just you get from the internet or just random noise you generate, forward it to DynoV2, try to see if you can make it work, try to see how do you check whether it works or not, try to visualize feature maps or these kind of things. This is a super good exercise, and I really encourage you to do it. It's super nice, and it's yeah, it's a lot of my work is that basically usually. Now this was about DynoV2. Now for the second part of this presentation, we're going to discuss something a bit different, something that's more recent. It's work that I did with my advisors that we published in last January, I think. This is called Cluster and Predict Latent Patches for Improved Mass Modeling. It's basically follow-up, and discussing this will allow us to go a bit deeper into self-supervised learning, especially in mass image modeling. This is interesting to understand a bit the landscape of self-supervised learning. Now, this basically, now for this work, we are quite a bit later. It's been 2 years since DynoV2. And what's obvious is that, as I discussed for annotation scarce domains, medical imaging, satellite imagery, biology, and for dense feature maps like this, these things are really dominated by self-supervised learning, specifically by DynoV2. Although I'm sure some people could make things better than DynoV2. DynoV2 is really a go-to for now. All of these are applications that were made using DynoV2, and things like dense key point tracking, depth estimations, these things are really helped by self-supervised learning. This kind of motivates the fact that we want to go further with self-supervised learning. We want to improve models. We want to really understand what's going on. But the issue right now is DynoV2 is complex. As you have noticed, I have kind of glossed over the specifics of the DynoV2 objective and the training details. It is a bit complex. This is a diagram from the iBot paper on which DynoV2 is based. It details the Dyno and iBot losses. DynoV2 has the third loss, which I mentioned, Cohere. It's a bit complex, and possibly because it's a bit complex, it's not very easy to scale. Now, of course, DynoV2, 1 billion parameters, it's already a bit scaled up, but the thing is, it's hard. You would like to go further, and already going to 1 billion parameters was not that easy. Also, there's a few suspicious things. Like, for example, those are feature maps of DynoV2 visualized, and you can see there's this kind of snowy texture that is a bit weird. It's kind of artifacts that is probably a result of the model just learning something weird, and probably the recipe is just not exactly right. But I would love to debug it, but I just can't because it's a mess. It's complex, and I cannot understand what goes wrong in such a big complex thing. The question is, can we go simpler? Can we strip down a lot of components and try to make something very simple, very understandable? And for that, let's rediscuss this DynoV2 objective. And you've got first Dyno, and Dyno is pretty well studied. It's very similar to contrastive learning we've mentioned. We understand it pretty well. We know what it's supposed to do, it's okay. Cohere, as I mentioned, it's a regularization. It's a very small loss and does not really affect the training dynamics much. We can ignore it, it's fine. iBot, however, is an interesting loss, in my opinion. iBot is a paper that was published about 6 months after the Dyno one original paper. It was SOTA, the iBot models, in terms of self-supervised learning of representations. It was state of the art until Dino v2 for quite a long time, actually. The iBot loss is necessary for Dino v2. We tried removing it, it just does not get the same results. These are the comparison table from the Dino v2 paper. Without iBot, it's just not the same scores, especially in segmentation here, 80-20K is segmentation. There's a gap of almost 3 points, which is non-negligible. But something I haven't mentioned, iBot is meant to go on top of Dino. This was built on top of Dino. It's a second loss that you add on top of Dino. It does not work alone. You cannot train a model just with iBot. And in my opinion, it's super weird. iBot goes further than Dino. It allows the model to learn new things that we were not able to learn without iBot and just with Dino, but it cannot learn alone. In my opinion, is very suspicious. It means something is, the iBot loss is not stable. It is maybe not the right formulation. Probably just the recipe is kind of wrong. I want to study it more. What's more, this thing flew under the radar. It's way less cited than Dino v1, v2, max autoencoders, this kind of things. If you know about it, it was a bit discrete, and so it was not well studied. It was not improved much since its publication, even though when we reused it in Dino v2, we did not touch it at all. We just added it and we did not optimize it. And so the question is, there's probably a better way to do this thing. We can probably do the iBot loss and get these points with more stability, etc. So let's study iBot. And to study iBot, we have to take a step back in mass image modeling. I mentioned that earlier. It's a recurring ID in self-supervised learning, and I think that's the. I wanted to talk about this paper because I wanted to discuss mass image modeling. I think it's an interesting point. Basically, the concept of mass image modeling is you've got an image, you're gonna remove part of it, and you're gonna try to predict what's missing. You cut out the rectangle in the middle, for example, and the model is gonna try to predict what you just removed from the context. If you think about it, it's a very interesting task, because to recover a missing part, you have to really understand the context. It's really a hard task that will make the model learn a lot of things. If you think about it, also, you might notice that it's very similar to what is done in language. In language, BERT was masked language modeling. That's what inspired mass image modeling. BERT was masking, removing part of a sequence, of a sentence, predicting what's missing. And it's a very similar concept, of course, to the autoregressive language modeling, like GPT style. Predicting the next token is also predicting a missing part of the sentence. So this is a very general objective that's very powerful and that's very appealing. Also, the success in NLP meant people wanted to try to make it work in vision too. But it's not easy. It's not easy. People have tried to make it work and gotten mixed success, especially for representation learning specifically. So the question is, how do you make good mass image learning? And so to answer this question, what we did was make this diagram that depicts the general framework of mass image learning. You've got an image where you have removed part of it. You have this question mark. You're going to feed it through your model. And your model is going to look like something, whatever, but it's something that takes these 4 things as input and outputs a prediction. This prediction will be compared to a target. The target is what your model was trying to predict, and there's a loss between them. You have to choose what goes here too. This target could be the raw pixels of the missing patch, but it could also be some more complex representation. If you had, for example, labels, you could want your model to predict that this is a patch of a dog, and therefore you get a much more semantic loss. Here we add, again, a missing box. We'll have to choose what goes here. How do you compute the target representation? How do you choose how you represent this target? So these are the three choices, and we go over them one by one. The first thing is target representation. You might say, simple, just use the pixel values. And that's the simplest case, and it's a very legitimate answer. Here is the diagram depicting it. Basically, given your full image, you just take the patch, flatten it, and it gives you a vector, and that's your target. And that's quite a few methods have done this. They have gotten mixed results in terms of representation learning. Matplotlib encoders were very interesting work for many reasons, but in terms of representation learning, they are not competitive. The reason is debatable, but in my opinion, I think it's because doing this, predicting directly the pixel values, means you will focus a lot on the color of the object, on the texture of the object, instead of focusing on the semantics. I would like the model to understand that when he sees the head of a dog, below that is the body of a dog. I do not care about him understanding that below that is black or green or whatever, or texture. I want the semantics. I do not care about the colors, this kind of things. Now, to get more semantic targets, what you might do is use a pre-trained model. You have your image, you forward it through an encoder, a frozen pre-trained model, and you get a better target representation that is much more semantic. And that's a very interesting idea. A lot of people have done this thing, and Bayit was one of the first works in machine learning and used a discrete VAE encoder. It worked kind of, but it was still very focused on pixels and textures. I mean, I don't know, the representations were still very bad. There are some other works that do that, but honestly, there's a kind of more philosophical issue that I've got with that, which is you're going to pre-train your new model using this frozen target encoder, and your new model is going to be hopefully better because you're trying to build a better model. But if your new model is better, let's just reuse the new model as a target encoder to train another new model that is even better. And once you get a better model that's even better, you can do that again and again and again. And you can bootstrap, self-improve your models into a better model. And a nice way to do that is to do that explicitly online. What do I mean by online? Well, you're going to use for the encoder, target encoder, you're going to use a version of the model you are training right now. Specifically, what is often done is using an EMA. EMA means exponential moving average. It's basically an average out version of the previous iterations of the model you're training. So the model you're training is going to be average. But weight averaging usually improves models. And honestly, it's very hard to understand why, but if you are curious about this, you can look up model soups or these kind of things. Averaging the weights of different versions of a model improves models. So by doing this weight averaging, you're going to get a slightly better model. And while your model trains, it's going to improve. And this EMA encoder is going to improve too. And so you will have this self-improvement loop that will improve the model, and you will just reach super good performance, hopefully. Except it's very unstable. Doing this self-bootstrapping thing means your model can run into a lot of trivial solutions or just weird regimes that do not work well. And it's very hard to make it work. So a lot of people have tried. iBot, it is part of this family. iBot does that, but there are other works like Data2Bake, IGPA, etc. We go in this direction because we think it's a good idea. And so for the rest of this presentation, we will discuss specifically this idea, trying to train a model that reinforces itself via machine learning in its own latent space, basically. Now, you've got the first choice. We use the EMA encoder, but then there's the second choice. What is the loss you use? And usually the exact loss you use is really not very important. The reason we're discussing this is because even though we could do direct, like just L2 distance or square distance between the two tokens, prediction, and target, or whatever, there is a small originality in the ibot work. That is, they use some weird MLP projection, so a multi-layer perception, a few linear layers with non-linearities in between, to project your prediction and the target into a different embedding space where they do the loss. And the target is projected with an EMA MLP of the prediction MLP. If it looks weird, it's normal. It's a bit surprising. The idea is coming from the Dino work. There is this in Dino that is kind of understandable in Dino. In Dino, you've got some interpretation of it. Basically, the head is doing implicitly a clustering of the embeddings. In ibot, this interpretation does not appear. In ibot, it's unclear what's going on. And therefore, my opinion was, okay, let's forget about this. It's complicated. I don't know what it's doing. Let's go back to the basics. If it was supposed to do a clustering in Dino, let's go back to clustering explicitly. What we're going to do is we're going to use an online clustering algorithm to convert our targets, vectors, into assignments. We just cluster them, get assignments, and then we're going to use a loss. But now the prediction is going to be trying to predict the assignment of the target instead of the target itself. It's debuggable, and I think it's a very important concept. It's debuggable in the sense that I know what every component is supposed to do. And so if something goes wrong, which is going to happen, because when you do research work, everything goes wrong all the time. When something goes wrong, you can just open up your model, look at activations before clustering, after clustering, whatever, visualize stuff, and try to interpret what's going on. In the previous thing with this MLP, we don't understand, we cannot debug. This is the proposed method, but the thing is, throughout this whole thing, I've discussed these choices, giving opinions. This is an opinion that I think the clustering is the right idea. We will discuss that empirically to show that this is just the right way to do it empirically. Before we do that, we'll just discuss the last design choice, which is about how do you do this prediction? What is the architecture of your predictor? And basically, we've got three choices. Again, it's a very small, appearing small choice, but it's very important in practice. It has a big effect. Here, basically, what you got is, in every case, these round colored boxes are a transformer. And so the first choice is use a single transformer that takes as input all the tokens, hash tokens, and mass tokens. And you then take the output above the mass token, and that's your prediction. That is the simplest idea, and a lot of people have worked with that, and they've gotten results with that. But there was something introduced by mass token encoders, MAE, that is interesting. What they propose is the patch tokens, the visible patch tokens that haven't been masked out, you forward them through a first transformer that is called the encoder. And this encoder only forwards the visible tokens. And so you gain efficiency because you don't forward the masked tokens. And then once you have encoded those into meaningful representation, use a predictor or decoder, it's called in MAE, where you add in masked tokens, and this predictor can be much smaller. And therefore, you save up on computation by removing the processing of the masked token. And then you get a prediction. That is a very interesting concept. We do that, but we just propose going one step further, which is, well, of course, the encoder does not need to see the masked token, but the predictor does not need to process further the patch tokens. They are already encoded into meaningful representations. And so the predictor can simply cross-append to the output of the encoder. And that is the architecture we propose, and that was used also in something called cross-MAE before. Now, again, this is what we propose, and what I'm saying probably seems to make sense, etc. But again, do not believe me just because I say things. These are opinion, and you are in deep learning, and nobody knows what they're doing. So only numbers on benchmarks actually count. Numbers on benchmarks, we ablate our choices, and we see that it works. basically, in terms of loss, we compare with different formulations. Basically, the IBOT formulation does not work, as you can see here, just does not really train. But the IJPA loss works, but it's just not as good by quite a long shot as the clustering loss formulation that we do. For the predictor architecture, same thing. I mentioned that fused predictor, so a single transformer works, but it's just much better to do this splitting where each transformer does its own job. One encodes the batch token and one predicts with the mass tokens. Something that was not mentioned here is that also there's the efficiency gain. Not only is it better, but also it's quicker to train. Each iteration is quicker. Now that you've got all these numbers, you can train a big model. We have designed our method. And so these are big result tables. Of course, there's a ton of numbers, and I don't expect you to read all that. But the gist of it is this CAPI model we train. We can train it either on ImageNet 1K, that is the first part here, or we can train it on bigger data sets, ImageNet 22K, Places, or La Vida, the one that we designed for DynaV2. And so basically, the interesting point here is it's much better than previous massive learning models like JPA, MAE, Data2Vec, whatever. It is comparable, but not as good as previous, as these grayed out models, which are models that are not pure massive learning. Also self-supervised learning models, DynaV2, you mentioned DynaV2 has these multiple losses. Except in some contexts, in some specific settings, for example, here when you pre-train on Places, CAPI is better on 8020K than DynaV2. It's already a very nice achievement because I don't think I've seen other models beat DynaV2 on 8020K KNN only now. It's pretty rough benchmark, but DynaV2 is very competitive. And so this is encouraging. CAPI does not replace DynaV2, but it gives encouraging results that seem to indicate that there is maybe something to be found in this direction. Now, before I leave you with questions, we do computer vision not because we like big table of numbers, but because we like pretty pictures. These are visualizations of the feature maps of DynaV2 and CAPI and other models. What are you looking at here? Basically, for each image, when you feed it to a CAPI or DynaV2, you get a feature map, meaning a grid of vectors. Each pixel here, each of these small squares, is a full vector of dimension something like 1,000, for example. The way you can visualize that is to try and project all of these vectors into a few components. And so you do that with a principal component analysis. You project these vectors to the first three components, which are the most preponderant component, the most prominent. And these three components, you show them as the red, green, and blue values of a color image. By doing that, you can observe a bit what do these embeddings look like, what does the understanding of the model look like. And so basically, you've got for the DynaV2 plus registers, what I showed before, this kind of snowy texture. CAPI has smoother embeddings. They seem to be cleaner. Other models seem to have pretty a lot of noise. Note that it does not mean that the embeddings are always bad. You can have signal that is hidden behind this noise, but it's still nice to see that CAPI seems to have very little noise. Before we get on to questions, I think we have a little bit of time to take away from today. Basically, first thing is self-supervised learning is basically unsupervised learning. It's one way to do unsupervised learning, where you use this trick where you create supervision from the data itself. A few common approaches, the few names that you should remember so that you can Google them later is contrastive learning and mass-image learning. Those are two approaches that work interestingly nowadays. DynaV2 is a very simple work where we take what works in self-supervised learning and we carefully scale it and tune it. We scaled up, we tweaked a lot. Again, elbow grease, it's necessary component. but nothing really novel. And one of the main strengths of the model compared to other models is the quality of the feature maps. In terms of mathematical modeling, what we discussed in the second part, it's very appealing. A lot of people want to make it work, but it's not easy to make it work well. It's very sensitive to a lot of small choices. It's very often the case in self-supervised learning and deep learning in general. It's not beating DynaV2 yet, it's not replacing it, but it's starting to be interesting and competitive. Now, thanks a lot for your attention. And yeah, if you have any questions, please do not hesitate now.
We do have some questions in the Q&A section, and maybe we can take one question from Q&A and one live question.
Yeah.
So it's in the bottom right, 9 dots, meeting tools. Then the next column, bottom, yeah, this one. So here you can find the Q&A.
I'm not used to that. Some very good size things. Elbow grease in Dino. Elbow grease meaning just trying hard and working hard. No, basically just Dino. Basically, when you do a work like this, in this kind of big scale project in particular, just spending a lot of time on every single detail, attention to detail, just trying every single thing that can be changed, trying everything, making sure you get reliable signal that tells you where to go one way or another. That is very important. It means also that a very important skill is efficiency in terms of experiments. Just being able to run a ton of experiments quickly, get signal quickly, making use of your compute, because often if you have good compute allocations, you can launch a ton of experiments at the same time and you can get overwhelmed. And so basically just managing a lot of experiments at the same time is an important skill. Tricky, yeah, okay. While we don't have DynaV3 yet, or do it, go ahead. 3 likes, fuck. I'm not in the Dyno team anymore since I've graduated and I'm not in Meta anymore. But yeah, it should come. It's coming. No, it's coming very soon actually, and but you'll get more signal very soon. The classification results comparison of DynaV2 clip for classification, both are varied in zero-shot manner. There's no zero-shot concept in DynaV2. Zero-shot usually designates doing a classification evaluation using text embeddings as a classifier. And so there's no text embedding in DynaV2. There's no text encoder. So you cannot do zero-shot in this sense. So what's done is linear probing. So basically, you freeze the encoder and you train a single linear layer on top of the encoder to predict the answer. And this single linear layer is trained supervisedly using the labels. Which are the top open source multimodal embedding models other than CLIP? Open source depends what you call open source, but let's discuss open weights, so the ones that you can download and use. I'm not expert in multimodal, but what we're going to call multimodal right here is joint text and image embeddings. Joint text and image embeddings. Right now, I think siglip2 is probably good, although I haven't tried it. And there's something called perception encoder that seemed pretty good from Meta. These two are, I think, open weights, and although I need to check for siglip2. And yeah, they are probably super good, but I haven't tried them. Note, multimodal models, I'm not talking about VLMs here. It's another thing. Doing data augmentation, how do you make sure that the image actually show the same as similar objects even though their embeddings close? Okay, so doing data augmentation, what you do is you take an image and you do 2 different crops of the same image. If you're unlucky, the 2 different crops could show 2 different objects that are very unrelated, but this does not happen very often. And even if the objects are kind of unrelated, they are still in the same scene, so they still have some things in common usually. But basically, the common thing you can imagine is you have a picture of a cat. You're gonna get one prop showing an ear, one prop showing a tail, whatever, and these two images are going to be related. How to know when we should use models like DynoClip versus encoder-decoder models like VLMs? So I think you should not have an issue on that, because you just can't fit the same problems into these two kinds of models. Basically, VLMs is when you want to be able to type in a question and get an answer. This is, for example, for chatbots, when you want to be able to give an image as a context for a discussion or these kind of things. Dino clip, pure embedding models. That's for building something with it, building like a machine learning model on top of it. So if you want to add a linear classifier, for example, to add a clustering layer, these kind of things. So first, to use them, you're going to have to be technical. If you're building an application for general public, you're not going to tell your users, here's the Dino v2 embedding, and they won't understand what to do with it. So if you just want the user to be able to ask any question, use VLM. If you want to embed images to do a very specific task, for example, one app I showed an example as is called PlantNet. It's an app where you can take a picture of a plant and get an answer about what species of plant is it. PlantNet uses a pre-trained encoder. This is the Dino v2 actually. PlantNet is about one specific task where the people who build it have technical knowledge, and so they can take a pre-trained Dino v2 and fine-tune it on this kind of thing. I hope that if these answers are not satisfying, please go ahead and re-add some stuff. I'll try to go through everything, but can you share some links to produce attention CS heat maps and images in with Dino v2? Maybe after the meeting, also depth. Yeah, because depth, you need a prediction head. You have a prediction head in the Dino v2 repo. I'll check out, but I think we have some notebooks in the Dino v2 repo that can show you how to do some of this stuff. I'll leave that unanswered to remember. Doing Excel training is encountering divergence about 150 above normal. Are you tricking this scenario and put data on something else? Additionally, what is your opinion on using model optimizers like Muon or NuP for SSL? NuP is not an optimizer, it's a parameterization. NuP is interesting, but I haven't had time really to do it properly. But basically, it's just NuP is rules to tweak your learning rate when you go up to bigger model sizes, mostly. Muon, haven't tried it yet. Why not? Thing with optimizers is, I'll be honest, since for the last 10 years, basically, since ADAM, every year has its trendy optimizer with people saying, "Whoa, it's gonna replace ADAM, etc." And in the end, ADAM stays. Optimizer research has become disheartening, even because just nothing works, and ADAM is always working. Even if Muon might be a little bit better than ADAM is so battle tested. Like, if you use ADAM, you know it's going to work. You have 10 years of people using it that tell you it will not completely break. But Muon, it might be that your problem is slightly special and has not been tested with Muon yet. And so Muon is a bit more risky, high risk, high reward. Still, I would maybe like to use it, but haven't tried it yet. So about divergence, no, it's not normal. Self-supervised learning can be unstable, but divergence is never normal. How do you trick in this scenario? First, it's never easy to answer, but the first thing you look at when things diverge is too high learning rates. Okay, is in medical application as Debatable and has to be proven. Basically, for medical applications, I don't do it myself. Basically, you have teams that do medical imaging research that work like in hospitals, etc., that work on applying models, proving that it works, etc. But then for proving it works, for example, in the US, you have to pass FDA approbation, etc. It's a hard process. Like it's meant to be safe. Ahmad, please stop me when needed, because I can keep answering answers, but if there is another lesson afterwards, of course, I don't want to take students from me.
Yeah, we can go on if you want.
Okay, I'll go on for a few more minutes. Can your method be extended to non-vision models, but in a cell domain? Okay. So my method depends what you call my method, dynamic or happy or whatever. In general, possibly, but it just remains to be proven. You know, if you do it and nobody has done it before, it's uncharted territory. Especially so EEG brain signals. I'm guessing this is like time series data. It's not going to be just a 2D matrix like an image. This is not easy to adapt, but possibly you can get something similar. For example, if you can get something like a tokenization of your time series data, maybe you can do something like CAPI. DynoE2 might be a bit different because you need augmentations that are very specific to images. Can self-supervised learning be used for anomaly detection instead of having labels for anomalies? I mean, probably. So I'm very unfamiliar with anomaly detection. I think it always seems like a very ill-defined problem for me. But I guess the first approach I would imagine if you train an SSL model on just a whole data set, then can you just look at your embeddings and see whether there's a small part of the embeddings that is far away from the other ones? Like just find the embeddings that are isolated, and those are probably anomalies, I guess. Yeah, for example, embeddings where the nearest neighbor is very far away, more than a certain threshold, but these are probably embeddings of anomalies. But uncharted territory, like I'm speculating here. Of course, I've never done it. The only way to know for sure is to try, honestly. Is it possible that we combine different frozen features from other models and scale DynoV2 up? Is possible to combine different frozen features from models? Yes. There's a work called Radio, that combines features from DynoV2, a clip, I think SIGLIP, and some segment anything. It gives interesting results. I think there's even a Radio 2. It works. Scale DynoV2 up. Scaling DynoV2 up is possible. It's hard, and you'll get more information with the V3, I guess. But yeah, basically, the thing with scaling up DynoV2 is you get easily issues, instabilities. Self-supervised learning can run into instabilities in general. DynoV2 in particular, as I mentioned, in my opinion, it's complex and messy, and so it runs into instabilities a lot. What is the reason for noise in the DynoV2 in the feature maps? Well, I don't know, and if you find it, you tell me, because I'm really interested. No, really, it's hard to say. I don't know. I think question is also, the actual good question is, why would there be no noise? And I cannot answer this either. Like, why would the model produce clean feature maps? Because of course you expect the model to produce clean feature maps, but that's a human bias. There's no good reason for the model to produce something or another. And yeah, so as long as I cannot explain why the model should produce clean feature maps, I cannot explain why it's not doing that. But this was one of my main research topics for quite a while. And although I've managed to fix some of the artifacts in DynoV2, not all of them, I've gone towards CAPI, this different line of research, to try and see if by making things simpler, I can understand better. That's, I think, one of the ways we can do making things simpler. How is this learning done practically? I mean, through which software? You code in Python and use the PyTorch library usually. I mean, basically 99% of deep learning research is coded in Python and uses libraries, usually either PyTorch or JAX nowadays. It could be TensorFlow too, but it's much less used nowadays. PyTorch, basically use JAX if you're at Google and use PyTorch if you're anywhere else. Because JAX is very good and even necessary to work with TPUs, which are the hardware chips that are produced by Google and used at Google. But most other people do not use TPUs, they use GPUs by NVIDIA, the thing that you have in most computers. And GPUs, you just use PyTorch, and PyTorch is very good and works super well. Have you seen drop pause paper? What do you think of increasing spatial and sending via SL tweaking? I think I've seen it. I don't remember exactly. I think I see the general idea. Using spatial understanding, that's really the goal. I saw in a slide you are projecting the data to MLP and calculating the loss. What's the intuition behind it? So this was what iBot was doing, and the intuition is unclear. My understanding is that the iBot authors did that because they modeled the whole loss after the Dino loss. And this was the case in Dino, but it was not, and it made sense in Dino. It does not make sense in iBot. To elaborate slightly on why it makes sense in Dino, yeah, this MLP projection kind of acts like a clustering, an online clustering. To understand better why, you could try and read the SWAV paper, SWAV, SWAV, like this. SWAV is a prior work upon which Dino is built and might give a bit of intuitive understanding of what's going on with the clustering interpretation of Dino. If SL is unsupervised learning, why not use unsupervised learning? So this is the first order approximation. SL is unsupervised learning. Second order approximation, as I mentioned, it's a type of unsupervised learning. It's a specific type where you get supervision from the data. Yeah. Do you think that any further elements on target fragmentation or the online model is probably the apex? I think online model is the apex, but that's an opinion. Like, I think online model is the way to go for the best mass learning, but I cannot be sure of it, and there's no proof of or data to. I mean, there's data to back this up so far because online model is what gives the best result for representation learning right now. But I cannot say for sure. I cannot prove that this is the best way to go. Visualization of dynamic learning. Okay, so I'm not sure what you saw, but there's something weird in the dynamic operational embedding that was caused by an aliasing artifact in the pre-training of DynoV2, where the position embeddings were resized without anti-aliasing. In DynoV2 plus registers that I did as a follow-up, we added anti-aliasing and it fixed that. I'm not sure this is what you were talking about, but in any case, it's an interesting tidbit. In general, positional embeddings of most model, what they learn is basically usually harmonics. So sine and cosine signals of the various frequencies. Usually you get this kind of stripe pattern. So what do sine and cosine look like in 2D? They look like stripes or blobs of different shapes. Basically, the idea is that if you have enough stripes or blobs in your position encoding, then when you stack them all to a big position encoding vector, you have enough information to localize each token. Yeah, didn't close my laptop since yesterday. Best book to learn more. A good question. I'm not sure. I'm not sure about books. Honestly, I don't want to recommend bad books. It's so about SSL. It's a recent literature, and I don't think you're gonna have a good SSL book. About deep learning in general, you have some recent deep learning textbooks. One textbook I used to study recently was the Bishop deep learning book, which is a this thing, Deep Learning Foundations and Concept by Bishop and Bishop. This is a good textbook that goes over basically most topics in deep learning, from foundations to very practical applications, including LLMs, different models, match coupling flows, these kind of things, GANs. Experimentation in general. How do you know when experiments can be scaled with large data? You don't. That's the nice thing. You don't. You do small experiments, and you try to gain an intuition about whether it's going to scale up or not. Sometimes you can say, okay, this experiment is heavily dependent on X. For example, yeah, this experiment, I have the intuition that it depends really on the embedding size. So if I scale up to a bigger model, it will change the embedding size, so it will probably not hold. So you can get some intuition, but it's something you build very slowly, and that's not easy to get. You scale slowly. You scale slowly in the sense that you do experiments at small scale, because you can do a ton of them, and that's nice. And then once you get some signal, you get to the next scale, and you get some more signal, and you see whether your signal was right or not at a small scale, etc. You scale slowly, but not too slowly, because if you spend ages on the small model, your intuitions will not hold up, and so you need to scale up. So it's just about finding the right balance. Scale up, not too fast, not too slow. Yeah. If I'm not mistaken, SSL. Yeah, we discussed that a little bit before anomaly detection. I don't have experience in that. I don't know of work doing it, but it seems like a very reasonable approach, especially for imagery, satellite imagery, but especially with limited labeled data. As I was saying, a simple approach could be train an SM model, or even use a pre-trained SM model. Like DynaV2 might just work to some extent out of the box on SM imagery. You can do that, and then try to do probably some classical anomaly detection methods, or just some dumb heuristics like finding the points that have the least nearest neighbors, or these kind of things. We found out any deceived codes where Cappy got cleaner feature maps than Dino. Basically, it's very unrigorous, but my intuition is that I think basically I cared more about this while designing Cappy, in the sense that basically while designing a model, a method, and while tweaking it, you look at some signal, you look at some feedback signal of whether my model is good or not, is this modification a good thing or not. In DynaV2, there was very little signal about the quality of the feature maps that was used. In Cappy, I use much more feedback signal on that. I use segmentation metrics, these kind of things. And so I went towards a model that has clean feature maps, whereas in DynaV2, it was less the case. Yeah. What is position embedding in your definition? Position embedding is anything that informs the model about the position of tokens. Why is it needed? Remember, a transformer is a model network that operates on a set of tokens. The tokens are indistinguishable in the transformer. There's no order in the transformer. And so you need to tell the model at what position was each of those tokens. If you give, for example, a sentence to a transformer, you do not put position embedding, it's the same as if you scramble the sentence. Same thing for images. If you give an image to a transformer without position embedding, it's the same as if you scrambled the patches of the image. So position embedding is anything that informs that. In our case, in the models I discussed, in Dino V2, it was a learnable additive position encoding, meaning for each position in the image, for each patch, you add to it, after embedding the patch through the embedding layer, you add to the token a value that is learnable. And so the model learns its own position embedding that is added on top of the image. In CAPI, I went to a different direction. I used rope position embeddings. Rope is something that is very common in language models, and it's a bit too weird to explain orally, but you can look it up. It will look weird at first. Yeah, it still looks weird even with some experience, but it's what's used nowadays in language models. Cookbook of self-supervised learning, yeah, true. Dino for spectrograms. Yeah, I think so. You've got, I mean, there's something called Dino SR, which is not Dino actually, but is probably on spectrograms. It is SSL on speech recognition, on speech data. Basically, there is SSL on audio data. I'm less familiar with the literature, but it exists. Yeah, as I said, if we can tokenize time series. Yeah. Specifically, can we use Dino on spectrograms? I think so. Note that in Dino, there is some color augmentations. There's no concept of color on spectrograms, so you cannot do it. But in terms of cropping, you can. You can probably just use Dino or Dino V2 out of the box on spectrograms, and it will give non-trivial results that kind of work. The exact performance, I cannot say really. Thanks for the session. How can I apply at INRIA for research internships as a final undergrad? Okay, let's answer this in a very general manner. How to get an internship? It's a super general idea. How to get an internship? Basically, I think from what I understand, because I'm not an expert either, from what I understand, you want to contact researchers directly. Contacting researchers is pretty easy. Once you know the name of a researcher, basically when you look at his papers, you can find his papers pretty easily. Yeah, his Google Scholar. Google Scholar is basically, so if you do, for example, Google Scholar, Timothe, that's me, you get my Google Scholar and you have the list of my papers. And usually when you get such a paper list, you can click on a paper, get the PDF, and you can get the email address in the papers. Here I put only mine, but often in most papers, they put every email address for the authors. So that's the first answer. You can get email addresses via looking at papers. Once you have email address, you want to send emails to a researcher that interests you. It's very good if you can have a specific topic. If you are very interested in working on X or Y, especially if you have experience, so either work experience, school projects, or just personal projects. Even if you just like try to work with model or this kind of thing. If you can send an email to a researcher saying, hey, I like this paper, I did this small project that is related to your paper, I tried re-implementing your paper, for example. This is basically super good, and I think the researcher is going to be interested directly. This is how you can get internships usually. So for INRIA, for example, you try to contact INRIA researchers. It's not a prerequisite. I've worked with their papers, but it's better. It's nice, and I think it increases your chances immensely. Also, regardless of the internship, trying to re-implement, like trying to reproduce a research paper is an extremely good exercise. Like even as a PhD student, even for me right now, you learn a ton when you take a research paper and try to reproduce it. So if you don't know what to do, it's super good projects to do that. Effective is SSL in self-driving cars. I don't know, because they don't say, the companies that do that. No, actually, you've got Valeo. Valeo is a company in Paris that does research in self-driving. They have very much interest in SSL. I think basically self-driving companies have interest in SSL. I've discussed with guys from Tesla who are very interested, but they don't say what they do. You've got also a company called Wave that does super good thing. Gaia 1, Gaia 2, you can look at these things. They're super interesting works. There are, yeah, basically SSL. Can you tell colorization help getting features? You can look at the paper colorful image colorization, and that's an old SSL paper from 9 years ago now, where it was one of the important SSL papers of the time, where basically they show that by learning to colorize images like that, you learn interesting features that transfer well to downstream tasks. So they have then tables where they show, okay, that's colorization results. I think they have transfer results somewhere. Top 1 class accuracy on image net linear classification, and yeah, you get some interesting results. Basically, it's not incredible by today's standard, but it's non-trivial features. Intuitively, it makes sense because to colorize an image, to colorize a picture of like a scene with trees and grass and sky and whatever, the model has to recognize some basic patterns. Has to recognize that this texture is associated with grass, and so that should be green. Flat texture is at the top of the image, usually sky, it should be blue. Bark texture should be brown, the bark of trees, and above this bark texture should be somewhere with a leaf texture that should be green, etc. You learn to interpret some small parts of images. PhD student in bioinformatics, any suggestion how to join Meta for R&D? What I was saying before, contacting researchers, basically. That's, I think that's the only way. Note that a lot of researchers, though, are bad with emails or just overwhelmed, and so they often do not answer. You can respectfully just remind them of your email. Like if you have like after a week without any answer, you can send them a reminder. Hey, have you seen my message? But yeah, if you send emails, as I'm thinking, especially in Meta, but if you send emails, there's a chance you will never get an answer. But you should still try. Note that Meta has not many positions, of course, and quite a few applicants. If you want to join Meta as a PhD intern, you can get internships, though that's something they do. Really good advice. Which paper should we implement? Which paper should you implement? That's a good question. Let's find something that interests you. The hard thing also is how to know your implementation is correct. Usually you want to reproduce the numbers that are in the paper, but often you won't have the compute to do that, especially to reproduce like SSL papers. I would say try to try to reproduce. You could try like coding a simple contrastive learning training, like here, like that. And even though you will not get the same results as the paper at all, what you can hope for is, can you get a non-trivial result? And can you get the model to learn something, anything? But it's not easy. It means you need to have something that is approximately correct. And so yeah, try to code that, run it on very small data sets, running on Cypher with a very small model, ResNet 18 or even smaller maybe. Yeah, try doing that, and yeah, I think that could be a very fine project. Use DynaVi2 image captioning. Yeah, but you need a captioner. A captioner meaning something that can generate text given an image. So that's basically VLM or this kind of things. So you need to plug DynaVi2 into another model and train them to work together. And in practice, in VLMs, usually it's not DynaVi2 that's used as an encoder. It's more like clip-style models. Thank you. You're welcome. Continue to explore computational neuroscience research at Meta. Yes, actually, very much, Vishal. if you want to do that, there's a lot of neuroscience research, not a lot, but there's a team that specifically does neuroscience research at Meta in Paris. You can look up the work of Jean-Rémy King. Is it? Yeah, it's with an I. This guy does neuroscience research at Meta. He's super cool, and his team is incredibly cool. Super nice guys. Permission to split possible objects into depth layers. Yep. Yes. The info is there. It's just the info is there in the features. It's just as a human, I don't know where. Like maybe there's one channel or a few channels, if you combine them, that encode this to some extent, of course, not perfectly, but it's just you need to find this. Yeah. So in Dino-E2, we trained a linear head to infer this, so it finds the right channel, the right direction in embedding space that corresponds to that. But once you can use this linear head to extract it. Nope, it's not open source, and it's very hard to open source this kind of things from inside Meta. I would have loved to. I think all the team would have loved to open source the dataset, but it was really not possible. From outside, basically, Lion is a good uncurated data source. Lion is very messy, so consider it uncurated. Note that it has a ton of legal issues from all the sides. But yeah, there's no LVD. Honestly, you don't need LVD. Just use ImageNet22K. It's really good enough. It's almost the same. We got almost the same results as LVD when using ImageNet22K in Dino-E2. You can check the comparison table in the paper. It's very close. Oh, I reached the end. There was some raised hands too. So if you want to unmute and
Yep. So I had a query regarding SWAV and deep cluster, basically on the clustering-based approach. And like as you mentioned earlier, you're using SWAV as an online clustering to replace the offline k-means. And since Dino is built on SWAV, and but I wanted to discuss about this SK, the synchron clock algorithm. Yeah, you have elevated that, and you have put it in the architecture that you use that too. So yeah, I wanted to get some details about that, about the clustering aspects, and how was the approach a bit different?
Yeah. So about this thing. So let me take. Can I get in this archive cluster? Yeah, perfect. So basically, the exact clustering we use in CAPI is very similar to things like SWAV, but without getting into too much detail, first thing I wanted to discuss, you mentioned SK, the synchron knob. Synchron knob is a complicated name that is scary, but basically, this is the code for a synchron knob. It's super simple. Basically, the idea is that the synchron knob algorithm is an algorithm to make a matrix sum to 1 on both the columns and the lines. And so the way you do it is that you will divide the rows by their sum. So the rows will sum to 1. And then you will divide the columns by their sum. And so the columns will now sum to 1, but the rows will not. And you will iterate on that. Just keep renormalizing one side, then another one. And doing that, you will end up with a matrix that sums to 1, both for the rows and the columns. It is a kind of normalization to rebalance stuff. We use it to prevent collapse and to rebalance the assignments. About the choice of algorithm, so CAPI was kind of derived slowly from iBot and Dino. So that's why the algorithm is very similar to something in SWAV. do I have actually the big diagram? There's a big diagram that includes the clustering. Yeah, this is the thing, and this is the online clustering part. And basically, the idea is that given all those tokens, so you have a tensor that is give batch size, so number of images in the batch, times number of tokens in an image, 196, batch size is 16K, times 1,000 dimensions, that's the dimension of the vectors. And passing it through a linear layer is the same as computing an inner product with a set of prototypes, which are the raw vectors of your linear layer weight. And basically after this, you can consider that the output of this linear layer, this inner product with the raw vectors, is a measure of similarity with prototypes, and therefore is a kind of an assignment score that measures how much every token is assigned to every prototype, meaning every cluster. And basically this assignment score will rebalance it so that the tokens are spread across all the clusters and they are not just too focused on one cluster. And then we'll compute a cross entropy. And by doing this cross entropy, basically what will happen is that we will force these assignments to become sharper, meaning we'll force the prototypes to move closer to the points that are assigned to them. And so these prototypes will stay good prototypes, are close to the data. And it's very similar to a mini batch game in a sense, and very similar to what happens in Swap. Does that answer the question?
Yeah, it does very much. Thanks.
You're welcome. Any other raised hand?
Can you talk about like what a normal day of work is like for you? Like, are you reading papers or are you like studying math? What do you find the most frustrating about your job? And like, is there a linear progression to the work? What do they expect you to deliver?
Yeah, that's a great question. Read papers not very often, maybe not enough. I'm not super good at that, but often I'm not very keen on reading papers. I mostly basically code experiments, launch experiments, debug experiments that went wrong, and or analyze results and communicate results. So coding an experiment is often pretty fast, although sometimes it can be long, but basically if you already have a code base that does the thing you're working on, often you do pretty small modifications and you want to see what it does. So coding an experiment is quick. Launching it, if you're used to it, it's pretty quick. You SSH the right cluster, you do the right commands. At the beginning, you forget always one thing and you always have to cancel the job and relaunch it, etc. But once you get the rhythm going, it can be pretty quick. Then you've got to wait for the experiment. But if you've already launched experiments yesterday, you have some results coming in. Some experiments are coming in, so you will check the results. And that's a bit more work because, I mean, in my case at least, often there's a lot of results analyzing. Like, I have a lot of trends, a lot of values, a lot of metrics, and I want to plot them one against each other and see. I want to do a lot of plots and see whether I get signal. And after I get some signal, I get some communication in the sense that I write all of my results in a experimental log, like a Google Doc, basically, which is shared with my advisors, and we will discuss it with my advisors. Either they take a look at my Google Doc sometimes, or next week at my weekly meeting with my advisors, we discuss the results he had, and we discuss like, okay, how do we understand that? What does it mean? Given these results, what is the next experiment we want to do? This is the gist of the experimental loop. You've got some other stuff sometimes, for example, I did a lot of work on just lab. I don't know if I can say lab, but basically just loading up models in notebooks and probing models, just opening up a DynoV2 or any model and forwarding images through it, examining activations, plotting activations against each other, etc. There's no experimental wait time here, so it's just you against the code and the notebook, and you just plot stuff and look at stuff and try to understand what's going on. You mentioned linearity, and no, of course, it's not linear at all. It's a very important thing about research is it's absolutely not linear progression. It is extremely irregular, and it can be super hard and psychologically because you can feel like shit, especially for PhD students, because often as a PhD student you are kind of alone, or not alone, but you have a main product that is your product. And so if the product is going wrong, sometimes you can take it personally because your own sense of worth can feel too associated with the way your product is going, if it's going wrong or not. And so, yeah, the fact that the research improvements do not grow linearly at all, and sometimes they can stall for months on end and you don't find anything, and every experiment you try does not work, can be super hard psychologically. And yeah, a lot of the PhD journey is about just learning to accept that and managing it. Yeah.
How do you come up with which code experiments that you're gonna do?
Well, first thing is you've got advisors for that. If you're in a PhD student or master student in a project, this is kind of the work of the advisors. They don't write the code and they don't run the experiments, but they should at least provide the ideas. Especially at the beginning of a project. First thing is when you arrive, you don't know what to do. You read about relevant things, but first thing is to define the product. Like, on what are we going to try and work? And the advisors can be very useful to say, hey, I've got this idea lying in the back of my head for quite a few months. I think it's super interesting. I think if you try it, there's a good chance it can lead to some interesting results. This is how you get going.
Thanks.
You're welcome. I mean, of course, also you can do the advisor work. Like if you can get good intuition, you can also define your own experiments and direction. It's a question of intuition, and intuition is always hard. And so if you don't think you have intuition, you can trust the advisors usually. Yeah, Lima?
Yeah, I wanted to ask, what are some important research questions to focus on for someone who is interested to do AI research and get into a PhD program?
So it really depends on the exact interest. But I mean, so I was going to say, yeah, if you want to work on self-supervised learning, I can give pointers, but this is a bit specific. Often people will tell you need to know what you want to work on, but honestly, when I was a master's student, I was like, I have no idea. I just learned about all of this. You tell me whatever, I will work on it. So right now, I mean, as a general rule, do not go towards completely niche things that seem to have no application or no use whatsoever. Because sometimes there are some fields that are not super useful. But also do not go towards overhyped stuff, I think. Not only because the hype can be just a bit bloat sometimes the hype is not worth it, but also because it means it's very saturated. If you try to do LLM research, I don't know, like Envision VLM research, a lot of things is very, very saturated nowadays. And it can both be very hard to compete and get a good results, and also very taxing mentally, because it means the field is super fast-paced, super stressful, etc. I liked working on self-supervised learning because it was not too much of a hype field these last few years, and therefore compared to like LM research, it was much more relaxed, I think.
Got it. So
Yeah.
in terms of self-supervised learning itself, what are some important questions or topics that you think would be good to address and focus on?
So I think the question is what works, and okay, basically how do things work? How does DynoV2 work? How does CAPI work? And how to make them better? That's the question I'm really interested in. CAPI was an attempt to simplify and improve DynoV2. Getting a bit there, but there are still some very weird things. There's some instabilities, very specific weird instabilities in CAPI that I could not solve, and are unsolved problems. But unfortunately, to work on that, you need a bit of compute, which is not easy to come by. But in some parts of academia or in industry, you can get that.
Thank you.
So yeah, to refine the answer, for example, CAPI instabilities, be precise, when you train a too big model or you train for too long, you reach a very specific model instability that is, I think, interesting to study. Like, why is it happening and how to prevent it?
Thank you so much.
Best advice finally as students who want to pursue research fields. I mean, I don't know where you are, what's this final year. I was in the French education system, which is pretty weird, but basically the way it went for me is that my last year of uni, my last year of master's, I had a master's internship. So I landed this internship at Meta, which was very lucky and were very nice. And often when you get a last year internship in research masters, these kind of things, you can convert it to a PhD program afterwards. It's often the concept. I know it's pretty different in like US curriculums and probably UK too, because often people go straight from bachelor's to PhD. So I don't know exactly how it works. I guess you can do research projects with teachers or these kind of things, maybe. Sorry. How does DynoV2 compare to the self-supervised learning models in terms of performance and efficiency? I often struggle with the concept of efficiency because honestly, the question of how fast do these things train is not often a problem because we train them as long as we can until they stop getting better, usually. The limiting factor is not really the time or the compute. It's just that these methods are very unstable. And so after a short while, if you keep training them, the performance goes down. It does not keep improving for some reason. So for example, DynoV2, we did not train it as long as we could have if we really went hard on the compute because it was just useless. It was not improving the model. So I don't know exactly in terms of efficiency, but yeah, usually methods are just trained as long as they can, and so we compare the best possible accuracy, whatever the training length. Number of papers or more programming experience in a specific field. I don't know. Programming experience you can get. I mean, I'm not sure I understand in what context. To get a specific internship or a job, in academia, papers are regarded. Like saying, I work with this is never going to be as regarded as seeing that you have made a paper on this. Because papers are tangible, they are proof. And so papers are like public proof that you have worked on something. And so they are a very important credential. More so, I think, than if you say you have worked on this. Of course, if you have not worked in academia before and you are an engineer, for example, and you have experience as an engineer, well, then people will understand and take your claim at face value. But you will not be able to get, for example, researcher positions usually by having only engineering experience. Me to intern with you. I don't have a job. I'm jobless right now, so no. Although I'm an incoming researcher at Meta, so I'm gonna have a job, but no idea if I'm gonna have interns anytime soon. Feels weird to say I'm supposed to be the intern usually, but yeah, no, sorry, I have no idea. But contact me again in 6 months, maybe. There's a difference between PhD at industry versus academia. So PhD in the industry is a very weird concept that is not very common. I was able to do it in France. There is a very specific way to do this. It's called the CIFRE program. And it's not exactly just in industry. It's a PhD that is jointly with industry and academia, where you are both affiliated to a company and to an academic lab. For me, it was with Meta and with INRIA. And it's something that's very specific to France. It's not easy to, there are not many programs like that in the world, I think, in other countries. I know Meta has PhD programs mainly in Paris. There's like at all times 20, 25 PhD students in Meta in Paris. A few in London, I don't know, 3, 4. A few in Tel Aviv, maybe 2, 3, I don't know. I actually have no idea. I know Google has a few PhD students, 2, 3 in Paris right now or around Paris. But yeah, it's pretty rare. About the actual differences, the fact that I was affiliated with Meta meant a lot of things. First, access to compute, a lot of compute, which is a big difference with academic PhDs. I think it's important to recognize it. It's also a bit different in terms of advising, I think, because at Meta, I had 2 advisors who had 1 or 2 PhD students in total. So basically, I had a lot of times with my advisors, but also my advisors also had their own research work to do. Whereas in academia, especially in the US, the advisors might be senior researchers who will spend 1 hour with you every month. I don't know. It's a bit cliche. I've never done it, but I've heard that sometimes the advisors have 15 PhD students, and it must be hell. But there's a difference in advising too. Also, of course, there's different in like working conditions, industry working conditions, and salary were really nice perks. Explainable AI and ML. Yeah, I guess. I mean, ML is machine learning. AI is artificial intelligence. These 2 things are usually synonymous right now, although these terms are a bit nebulous and not very well defined, especially AI. Explainable AI, it's very vast concept, but basically machine learning, often ML also designates classical machine learning, so things like logistic regression, linear regression, these things that are more in like statistics textbooks. The explainable AI uses quite a lot of that right now, especially things like mechanistic interpretability, where they use things like sparse dictionary decomposition, was very much studied in ML in the 2010. Sparse dictionary decomposition can be very interesting to decompose latent activations of models into concepts. Things like sparse autoencoders, if you've heard of that, they are very hype at the moment on Twitter, etc. Yeah, so there's a link, I guess. Right. I spent a lot of time, I think. I don't think there are other questions.
Yeah. Thank you so much for taking out so much time. I really appreciate it.
A pleasure. Thanks a lot for having me.